Got a bio test.
Alright.
Quiet on the T.
Quiet on the T.
Quiet
On the
T,
calculus
golf
T.
reference.
We're about to make a 357-yard calculus drop. On calculus greens in the state of calculus and the country of calculus.
There you go. Okay, so if we're trying to find the area of the shaded area. Okay, now, and I'll tell you where we're going with this. I hope by the end of the year we can get to a place where we will do some things like, this is gonna blow your mind, we're gonna do some things like, let's say what happens if we take that shaded area and we revolve it around an axis to create a three-dimensional shape. What's the volume of that? So that's where I'd really like to get to that. That's pretty ambitious, but I'd like to get to that by the end of the year. That's kind of that's my goal. But so to start there, these are called volumes of revolution. They're a really cool part of calculus. To get there though, we got to first look at how to capture these areas that are bounded by different functions. Okay, so this, if it's an area, it's unless we can add it up geometrically, it's going to be an integral, right? So what do? How are we going to get that area? There's a bunch of different strategies you could take here.
Find the area of the rectangle.
Okay, so one thing you could do is you could do an area by subtraction, right? You could calculate the whole big rectangular area. So we're doing, I guess, like this area right here. Like that whole thing. And just subtract away from that the area under the red curve, right?
Yeah.
Now the area, that rectangular area is easy to calculate. That's just geometric. But the red area we would need, to take an integral, right? So if we do it that way, it just looks like what? What is the area of that rectangle? Pi over 4 times 4, so pi, right? Okay. So we end up with pi minus. Now what about the red area? What's that going to be?
Like 3 seconds.
Okay, so we got to take the definite integral of this, right? Of 3 cosine x plus 1. Now, we got to put that in parentheses, right? Technically. Does that make sense?
Yeah.
Okay. Dx. From 0 to pi fourths, and that should do it, right? So to take that integral, we're going to have to integrate term by term. What's this first term give us? Plus x. Oops. Evaluated from 0 to pi fourths. What's the value of that expression at 0? 0, which is convenient, isn't it? So really it's just the value at pi fourths minus 0. So that's equal to, what do we get? So pi minus
3.
At pi fourths we get,
2.
yeah, okay, because sine of pi fourths is square root of 2 over 2. So 3 radical 2 over 2 plus pi fourths. So pi, and we're subtracting that whole thing, right? So pi minus pi fourths is pi fourths minus that, right? Okay, does that make sense? Hold it.
It'd be still negative.
It'd be 3 pi over 4.
Yeah.
We'll go minus the fourth, 3/4.
Oh, yeah, you're right. Good job. Thank you. You're right. Very good. Okay, yep. Okay, make sense? Okay. You could, that's the easiest way to do it, I think, because it's a geometric area. Just to kind of prep you for how we're going to have to do stuff like this in the future, you could also look at this as one big integral. Okay, so let me just show you something here. So we could define this top function as 4, right? That's an easy one. So we could take this whole thing then as the integral of 4 minus 3 cosine x plus 1 dx from 0 to 5/4, right? Does that make sense? Okay, and then we could simplify this integrand a little bit. I could distribute the negative, and that's just gonna give me, there's my 3, right? 3 minus 3 cosine x, just make it one different integrand. Okay? Either way. Does that make sense what I just did?
Yeah.
So we've got, let's talk about that for a second. So we've got the area under the blue line. That's this guy, that's the 4, right? We can think of it this way. Here, here's another way to look at it. We've got the integral of 4 dx from 0 to 5/4 minus the integral of cosine x, 3 cosine x, plus 1 dx from 0 to 5/4. Because these integrands share the same variable and the same limits of integration, we could just include them in one big integral. Okay? Make sense? That's how we're gonna eventually have to do these when we start to do volumes of revolution. I don't wanna jump the gun too much with this, but when we eventually do volumes of revolution, whether it's this year or you guys do it next year, you're gonna have, like, if this is, for example, is your axis of revolution, then what you're gonna have to do is you're gonna have to carve out little slices that are gonna get rotated around this axis to generate little washers, right? And those washers are gonna get stacked together to make the eventual shape that you make when you rotate that whole area, revolve that whole area around this external axis. And so to do that, you have to define something like this. Okay, but we'll get there when we get there. You'll get there when you get there. But my point being that this is an inevitable step for you at some point. Okay? All right. What else? What else is causing trouble in any of this stuff? How about the new assignments? Use substitution. What's that? Haven't got to yet, okay. The use substitution one, I don't think you're gonna have a lot of trouble on that. I really don't. It takes a little getting used to, but I think you're gonna be fine. Remember, there's the one thing that people have a tendency not to do on that, in my experience, is, let me just maybe look through one quick review problem, a definite integral. So what would I do? Oh, jeez. You know your desk's getting a little too messy. Why didn't we just?
I guess that comes down to garbage.
Okay, how about,
They did, but I'm not gonna make that mistake twice. I'm gonna take my time walking up the stairs. That was kind of an nerve. Just to get out of here. No, I was going down.
okay, real quick, do we need, yes or no, do we need a use substitution? Say it again? No. How can we do it without?
Yeah.
I'm hearing a yes.
Oh, sorry.
Oh.
Yeah.
Yes?
Yeah.
Okay, compare that to, say, a problem like this. What if we had something like the integral of x minus 4 times the cube root of x dx? Okay, one of those requires a use substitution and one does not. This one
That requires.
This requires?
Because of the parentheses?
Does not.
This one does not, does it?
You can distribute it.
Good. This time, now, I want you to see the difference here. This time, we could distribute this one factor over this sum or difference, right? And that's really just next to the 1/3, isn't it? Right, so I could rewrite this as the integral of x to the 1 plus 1/3. Simple. Just power rule, right? No big deal, okay? Because we can distribute over a polynomial, right? That's easy to do. That's our distributive property. Okay, can we do the same thing up here?
No.
No, we cannot, because we can't distribute over a radical, right? That whole x minus 4 is being taken to a 1/3 power, so we cannot distribute that x. And so this one is more problematic. This one does require a u substitution, doesn't it? The argument, whatever's inside that radical, we really need to be able to write that in this way as a single thing. Call it u, right? So this one does require a substitution. What's our obvious substitution? Yeah, x minus 4. So we'll make the substitution. U equals x minus 4. So what's du?
X minus 4 dx?
No.
One.
1 dx. Good. Okay, so we end up then with the integral of the cube root of u du, but we still got that x out there. It's been a while since we looked at this, but that's an incomplete substitution. So what do we do?
Forget it.
Okay, this is a case where we can save the day, because it's easy to solve for x in terms of u. Now, sometimes you can't. Sometimes if you get an incomplete substitution, it just means it didn't work. We have to try something else, and we don't know very much else yet. But if we solve for x there, we just get x equals u plus 4, right? So we can complete the substitution and get u plus 4 times u to the 1/3 du. And now we can do that problem, right? Does that make sense?
Oh, yeah.
Okay. All right, so what about,
Oh.
What was it, times u to the 1/3?
yeah, I mean, we could do that. Do you want to do that one? Or, I mean, really all you do there, I think you guys are fine with this. You just distribute that u, and I get two different powers of u. Well, maybe, do you want to finish it?
Yeah.
You finish it? Okay. So what do I get if I distribute the u to the 1/3? U to the 4/3 plus 4u to the 1/3. Okay. So what do we get for our antiderivative then? We take the,
So it's gonna get
3, well, hold it.
No, it's gonna get 7/3.
Okay, so we're gonna get a 7/3, u to the 7/3 over 7/3, which we would instead write as times 3/7 plus yeah, 4, so I'm gonna get 4 times 3/4, right? So what's that?
12/4.
Okay, 12/4 is just what? 3. Right? What do you buy that? Okay, and then what's the last step? Yeah, plug x back in. Good, so we gotta go up to our original substitution and reverse that. So we get x minus 4 for our u's. Done. Okay, no big deal. All right, how about one like this? What if we have Suggestions? Same kind of problem, right?
12.
We've got something too complicated under the radical. We have to simplify what's inside that radical, don't we? Okay, so what's our substitution?
U equals 6 times 1.
So what's du?
1
So du equals dx du. Okay, so we end up getting then, if we make that transition, integral of square root of u, right? Times du times x squared. As x goes from 1 to 5. Right, so what do we do now? It's all for x. So what's x equal to? U plus 1. Okay. Okay, so we can make that transition, right? So then we end up with, if we do that, we get the x squared becomes the quantity u plus 1 squared times u to the 1/2 du. What about our limits? Do you want to leave them as x's? We want to switch them to u's, because if we leave them as x's, we have to take the integral, reverse the substitution, and then substitute x, but we can make this much easier. Instead, let's just substitute, or let's just change the limits of integration from x's to u's, and then we can just get our answer, because it's just going to be a number answer, isn't it? A definite integral is an area, it's a number. We can get that number with, just by using this red integral instead of having to go back to the black integral, right? So when x equals 1, what is u? 0. Sure, we just go up and go to our substitution equation and evaluate, right? So we get 0. When x is 5, u is 4. And that's all we have to do, right? Okay, we don't have to switch back. So how are we going to do this one? What's our strategy going to be? Yeah, we're gonna have to expand the u plus 1 squared, aren't we? Get 3 terms, distribute the u to the 1/2, and that makes it really simple. Then that just makes it 3 terms that have, fractional power. It's a big deal. We'll just use the power rule, right? Make sense? Okay, so this ends up looking like, so we're gonna get what? U squared times u to the 1/2 would be u to the 5/2, right? Plus 2u times u to the 1/2, 2u to the 3/2, plus u to the 1/2. There it is, right? Okay, so if we take the integral, what do we get? First term? What power are we going to get? U to the 7/2. We're going to add 1 to the exponent. So u to the 7/2 times 2 7ths. U to the 7/2 divided by 7/2. It's times 2 7ths. Plus u to the 5/2 times 2/5 times 2. Good, so it's plus 4/5. And then finally, u to the 3/2 times 2/3. Good, 2/3 from 0 to 4. But conveniently, what's the value at 0 of everything?
0.
Right? So all we have to do is evaluate at 4 and we're done. All right, so we just get 2 7ths times 4 to the, okay, what's 4 to the 7 halves? 128, why?
Yeah.
But we don't even need a calculator for that, how come?
Do the square root of 4 times.
Ah, good, because 4 to the 7 halves is the same thing as saying 4 to the 1 half to the 7th, right? Remember, when you're dealing with a fractional power, you always deal with the radical first. So 4 to the 1 half is what?
2.
2 to the 7th is 128. Okay, well, if you know 2 to the 6th is 64, which is one you'll know. Then 2 to the 7th is just 2 times that. Okay, so we get 2 sevenths times 128. Plus 4 fifths times, what's, okay, real quick, what's 4 to the 5 halves? 32. Plus 2/3 times 4 to the 3 halves? That's it. We could, turn that into one big fraction if we want. That's our answer. Okay, just a number. All right, good stuff. Okay, how about one like this?
Most of them.
Okay, so let's say this is an integral that you guys will know how to do. You don't right now, but you will. But we don't have to do it now, so let's just use the trapezoidal rule, okay, to find the area under function 1 over x from 1 to 3. Now we want to do this so that our error is less than or equal to, we want to find the minimum number of trapezoids that makes our error less than 0.0000, 4 zeros and a 1. Okay, so what do we do? So we're not even really doing the trapezoidal rule yet. Right now we're just trying to find the number of trapezoids. I don't remember what it is, but you remember the formula or that we got to.
B minus A over 2F.
It's something like
A
that.
minus A over, or to the third minus N, 12N squared.
There you go. Okay,
Over
so it's
12N squared.
the error formula. Good. So we need the error formula. We need
Times
the trapezoidal rule error formula, which tells us this: the error is less than or equal to B minus A, and it's B minus A, was it
Oh, to the third.
third? Yeah,
Or
okay.
to the-
Cubed over 12n squared. Times that weird deal, right? Times the maximum
the absolute value
of the absolute value
of
of
the second derivative of x.
right? On our interval, which is from 1 to 3. Okay, so we got to do, now this is really easy to calculate here, isn't it? We know what's B.
3. Isn't it?
Yeah, what's A?
1.
1. N's what we're trying to find, right? So the only thing, and what's the error that we're gonna, yeah, there it is right there, right? There's the maximum allowable error, right? So We just need to, the only part that we're missing is this weird guy right here. Okay, so what's f of x? 1 over x, good. So then, which is x to the minus 1. So what's f prime of x?
Negative x.
Good. Okay. How about f double prime? 2x to the negative 3, which is the same as 2 over x cubed. Okay? All right, so now, how are we going to analyze this? We want to know where is this function, the absolute value of this function. Well, it's always positive from 1 to 3, isn't it? Right, so we don't really need the absolute value bars. But we want to know where it's going to have its maximum value. What's your thinking on that? We don't have to really do very much. If we think, we kind of think our way through this. What do you think? What do you think? Stuart, I got a question for you. So if this is the function that we're analyzing, this is our second derivative, and we're going from x equals 1 to x equals 3, why is the denominator important there? What do you think? Try to find where that's going to be its biggest.
Because a lower number is gonna be a higher.
Good, because it's an inverse function. Good, so the bigger the number on the bottom, the smaller the second derivative, right? So if we're going from 1 to 3, where is this obviously going to have its biggest value? At 1, sure. We can see that, can't we? Okay. So we know that this value is going to be at f double prime of 1, which is what? What is 2? Yeah. So 2 is what we're plugging in for all that junk, right? Okay. So we end up with then b minus a, so 3 minus 1 cubed over 12n squared times 2 has to be less than or equal to 0.00001, right? We can simplify that. That's just 2 over 12 just makes that a 6. That's just 8, right? 8 over 6 is 4 over 3. So this whole thing just becomes 4 over 3n squared is less than or equal to that. How do we solve for n again? Okay, well we gotta flip both sides, right? And that, now, we don't even have to turn that, what if that was some number, some weird number like, you know, instead of a 1 at the end, what if it was like 5-7 at the end or something? It may not be convenient for us to always write that as a number. In this case, we know that's just going to be what, 1, 2, 3. So it's just going to be 100,000. But it may not always be easy to make that transition. You don't have to though. You're gonna have to plug this into a calculator to find n anyway. It's going to give you back a decimal value. So why not just do this? In general, you know, we could. This one we could kind of skirt this issue, but in general we could just flip this side. That's going to change the direction of the inequality, right? And over here, just put 1 divided by our decimal. It's fine. Calculator doesn't care, right? And so now to solve for n squared, what do? Multiply by 4, divide by 3, right? So we end up with n squared is greater than or equal to 4 over, what's 3 times that decimal? Right? Square root both sides. And that's our answer. Somebody throw that in your calculator and see what we get.
No.
I got this.
Shut out.
403. Okay. 365.148.
Okay, so what's n need to be? 366. Yeah. Okay, big value of n. So now let's actually find that area. Do we have time? Yeah, we can do it. Let's find that area using the trapezoidal rule. So we got n. We got our original stuff. There's our function, right? So let me grab, well, let's go to the next page. I can remember that. So we're trying to approximate. $366. Okay. So now we got to set up trapezoidal rule stuff, right? So first things first, what I think you ought to do on these is just start off by just writing down the trapezoidal rule. So what is it? And this is definitely, it's a huge number for n. We want to write this in terms of sigma, obviously, right? So what do we get? So B, what was our multiplier up front? B minus A over 2n, good, times. Good. Plus.
2.
Good. 2 times that interior sum. Good. 2 times the sum of, good, f of x of I, which is just f of A plus I delta x, right? From 1 to, good, n minus 1. Okay, so we got our f of x, we've got our n, we know A and we know B. What is, let's just add a couple little things here. What is delta x for us? Say it again, yeah, right? 3 minus 1 over 366, so that's 2 over 366, so 1 over 183. Good. Okay, so we know delta x. We know A, we know our function is what? 1 over x. So we ought to be able to make this transition then. So we get 2 over 2 times n is 366. Right, 2's will cancel. Times, what's f of 1? 1. Plus, what's f of 3? Plus 2 times the sum. Okay, so A plus I delta x is just going to look like, we've just got f of 1 plus I times, what did we say that was, 1/183rd? Does that make sense? Okay, so what's f of hand? 1 over hand, right? If f of x is 1 over x, f of hand is just 1 over hand, right? So we're adding up here then the sum of 1 over 1 plus I over 183. Does everybody see that? Yeah. Is that making sense? If f, because remember f of x equals 1 over x, so f of 1 plus I over 183 is 1 over that. Okay, and we're going to add that, you told me, from 1 to n minus 1, which would be 365. So this ends up being just a big calculator problem. All right, so let's put this in our calculators. Okay, so tell me what to type here. Okay, and I'm not going to be fancy with the fraction template. I'm just going to use parentheses, it's quicker. 1 divided by 366 times quantity, right? 1 plus 1/3 is 4/3. 4/3 plus, now what? 2 times, how do I do the rest of this?
The math.
Okay, so I go math, and was it 0? What did I do? Oh, there we go. I just can't see it. All right. Goes there. I, but we don't have access to an I, so our only choice for a variable is X. So that's our index variable from 1, 365. Yeah. And then it already opens the parentheses for us for the sigma. So yes, we got 1 divided by the quantity. So I'm going to open a set of parentheses. So we need parentheses around, whoops, around that bottom building. Right, so what's that going to look like? 1 plus, yeah, X divided by 183. Okay, there are the parentheses for the sigma. But what else do I need to do?
You gotta close.
Actually, those aren't even the parentheses for the sigma, are they? Those are just the parentheses for the bottom, it looks like. Okay, yeah, so we need to close the sigma. That looks weird. What's that? What happened to our sigma parentheses?
You need to put it inside the work brand.
What is it called?
Yeah.
What, somebody sees what's going on, what do I have to do?
So the parentheses after 183 is the one
That's
for
the one that
the
adds
sigma.
the sigma.
That's
have
the
to
one
put
for the
another
sigma,
one.
what about this guy right here though?
You have to put it
That's
inside the other one.
parentheses.
Oh, we already had those there, I got you,
Yeah.
I got you, you're right, yep, very good. So remember, you gotta hit second insert, I guess it did it for me, there we go.
There we go.
There we go, perfect. Okay, so there's, and then it automatically had the sigma ones there. And then I gotta close the script, right? Script. These guys,
Oh, okay.
remember those, we got these parentheses enclosing the whole interior of the trapezoidal rule, okay? That should be it, right? Did it do it?
My calculator took a while. 365.
Yeah, it might take a little bit. I don't think mine's doing anything. There it is. Now it's thinking. Is that what you got? Okay. So that's the actual answer. I mean, that's the trapezoidal rule answer. Let's check the real answer and just see how close it is. How would we compare that to the actual answer? What was our function again? Well, right there, right? So I could just go math 9, is that right? So 1, 3, 1 divided by X. And look at that. Then we said the error had to be no greater than 4 zeros and a 1. Well, let's check this. 1, 2, 3, 4 were the same out to there. And then the next one is the same also. Right? So it made it. Okay. Isn't that cool? All right.